Good morning, Year 12. Today we're going to cover the topic of a parsec and distance measurements in space and on a cosmological scale. So we're going to start out by thinking about the topic of parallax. So thumbs up if you remember parallax. I have no idea if you're doing it, but put out your thumb at full stretch against a distant background and close one eye. Now shift to the other eye, backwards and forwards. What do you see? Hopefully what you're doing is demonstrating parallax to yourself. Parallax changes the apparent position of an object against a background when you change your perspective. So when you're looking through your left eye, your thumb is covering a part of the background, which is towards the right. When you swap eyes, your perspective changes. So the apparent position of your thumb against your distant background changes. Have another go if it didn't work for you first time. Make sure you're happy with the concept of parallax, the apparent change in position of something due to a change in perspective. We have, of course, come across parallax before in science. We're talking about parallax error. So when you're measuring, for example, the height of a liquid in a measuring cylinder, you need to make sure that your perspective is always in line with the top of the liquid, with the meniscus. Not a physics concept, admittedly, but lots of us do chemistry. I'm sure that'll be something we use quite often. Same thing here. When you shift perspective, the position of your thumb changes, just like when you shift perspective, the position of the meniscus changes. Whenever you have an image in which perspective has changed, you'll get parallax. These are two photos with a different starting position. And hopefully you'll see that everything is shifted position. The bin, the bike, the bench, and the man have all shifted a lot. Slightly further back in the background, the trees in the middle distance have shifted somewhat. If we look at the spires further back, they've shifted only very slightly. And going further back to the distant background, that's what we're measuring against. So that's barely shifted at all. So hopefully you can see that the closer something is to you, the bigger the parallax effect, the more it shifts position. So this is why we're talking about parallax now. The amount of parallax depends on the distance of an object. So if you measure the parallax, you can tell how far away that object is from you, as long as you know how much your position has shifted as well. So in this case, by comparing these two photographs, we can say, well, the person with his bike is much closer to us than the spires in the background. And obviously that's clear to us because we're used to having perspective. But if you're talking about point sources of light like stars, that's actually a really useful result. Closer things have a larger parallax. This is just another diagram showing the same concept as the thumb one. When you shift position, an object appears to shift against a distant background. So, in this case, the star-shaped object appears to be against the red background from one viewpoint, but the blue background from the other viewpoint. The other thing to mention is that the bigger our shift in viewpoint, the bigger the parallax effect. So if we were to move our viewpoint only very slightly, we get a very small parallax. So it'd be difficult to measure. So when we're thinking about stars, we have to have the maximum parallax possible. And you could come up with ideas of, say, having telescopes on other sides of the country, or other sides of the Earth, but even then, that's not a big enough shift in perspective to give a measurable parallax angle. We're going to have to think much bigger. And thankfully, we can. And we can because the Earth orbits the Sun. So, over the course of half a year, the Earth shifts from one side of the Sun to the other side. It rotates through 180 degrees. And that is the perspective shift that gives us our stellar parallax angle. So this diagram shows us the angle that we're measuring and the apparent shift of a nearby star against a fixed background of distant stars. The parallax angle is actually half of that angle. Why? Well, it makes the maths a bit easier, and frankly, astronomy has all sorts of strange conventions. The parallax angle of a star is half of the angle moved against a background of very distant stars over the course of 6 months. That's our definition of parallax angle. Just to make it very, very clear, if you're further away, then you have a smaller parallax angle. Remember that applied to the man in the foreground with the bin, close, large parallax angle. Spies in the background, distant, small parallax angle. Close stars will have a large parallax angle. Stars that are further away will have a smaller parallax angle. Hopefully that animation showed it nicely for you. So, we're doing this to be able to define the parsec. So, what's a parsec? You can look at the language involved. There's par and sec. So, yes, the par means parallax. What does the second mean? So, our definition of a parsec requires us to have a look at a very specific part of this diagram, which is this part here. We'll look at it in more detail now. One parsec is the distance at which the parallax angle of a star is 1 arc second. Now, we might not be familiar with arc seconds. Seconds are obviously measurements of time, not angle, but arc seconds is a standard measurement that we use in physics. Degrees are too big, is basically the problem. 360 degrees in a circle, but that's a gigantic angle when you're talking about these tiny shifts of stars. So instead, astronomers use arc seconds. So 1 degree is split into 60. Each of those is an arc minute. And each arc minute is split into 60 arc seconds. So that means that each arc second is 1 3,600th of a degree. Again, the reasons why we do this instead of using decimal parts of degrees, historical. So this is our definition of a parsec that you will be required to trot out during an exam, pretty much word for word. A parsec is the distance to a star with a parallax angle of 1 second of arc. Note that the distance between the Earth and the Sun here is 1 astronomical unit, 1.5 times 10 to the 11 meters. An AU is just the average distance between the Earth and the Sun. If you're actually doing these measurements, you have to take into account the fact that actually Earth's orbit isn't circular, so sometimes it's not exactly 1 AU away from the Sun. You have to choose the right time of year or make a small correction for your different base length. Okay, why are we doing this? Well, we're doing it because it's really, really easy to work out the distance to a star in parsecs when you measure your parallax angle in arc seconds. The distance to a star in parsecs is equal to 1 divided by the parallax angle in arcseconds. Very straightforward. Have a go at a couple of examples now. Pause the video so I don't move on while you're trying it. Okay, hopefully these are the answers that you got. 1.3 parsecs, remembering to round to 2 significant figures, and then MPC means exactly what we think it does. Mega parsecs. So 0.77 times 10 to the 6 parsecs. So your parallax angle is, well, I won't read out all the zeros. To get an idea of what a parsec is, this is how I think of it. The distance between stars is usually a few parsecs. So, if you're a Star Wars fan, the Millennium Falcon did the Kessel Run in the distance between some stars that are quite far apart, or maybe 3 or 4 stars distant from each other, something like that. Similar sort of magnitude to a light year. Alright, here are some research questions for you to have a go at. I'd like to spend about half an hour researching this. Try to get as many of these done as possible. Start at the top and move your way down. I don't need you to write a long report on it. You can copy and paste directly from your sources as long as you reference them. Most of these things will not come up during the exam. They're just to provide more flavour to our understanding. So please don't spend an enormous amount of time on this, just about half an hour. Once you've covered a few of these research questions, there are some past paper questions I'd like you to attempt. I will upload those onto Teams ASAP. Enjoy!